Hi everyone, this video is to go over page 4 of Midterm 2 for Chem 3A in fall 2019 at UC Berkeley, taught by MaryAnn Robak. This is Chemical Structures and Reactivity, by the way. So here we go. We are on problem, what is this, 3? Yeah, 3F, and it is the first problem on page 4. So let's dive in. So we're on number 1 for 3F. And we see this starting material right here and this ending material. Let's see what atoms are preserved. So we've got this R, that's going to be the same R right here. We've got the oxygen and the carbon that's separating them. That's still the same here. And we've got this carbon right here. What's the difference there? The difference is that this bond is no longer there, right? Yeah, there's still a bond between these two carbons. Let's call this carbon 1 and carbon 2. There's still that bond there, but the bond between carbon 2 and oxygen is gone. So what do we need to have? So all of this material, all of these atoms right here, must be the other reactant because they are not to be seen in this reactant. So let's go ahead and write that in there. That's going to be our other reactant, NH2, and here the nitrogen does not have a plus charge because it's only making 3 bonds, and it has its other lone pair. And let's see, let's number these other carbons too. That's 3 and 4. So that's 3 and 4. And then there will be the oxygen here, S, double bond O, and single bond O, negative. Okay, and so we see that this bond is breaking and it's going onto the oxygen. How do we know that? Because this oxygen ends up with a negative charge at the end. So the reactive orbital is sigma star CO here because the sigma bond is breaking. That's why it's a sigma star, and then it's between carbon and oxygen. So that's that. And then we know that it's that's going to form intermediate carbocation right there. So it's SN2, so there's not going to be an intermediate, but we know that that carbon would have a plus charge, which is why we know that the lone pair on the nitrogen is what is attacking that carbon. And so it is the non-bonding nitrogen sp3 lone pair that is going to be reacting here to form this product at the end. And so the nitrogen is the nucleophile. It's donating its lone pair to create a bond. And this material over here, the molecule over here on the left is going to be the electrophile because it is getting electrons from the nitrogen to make the bond. Okay, so we are now going to draw an orbital interaction sketch with shading and orbital labels that shows how the reactants in reaction F approach each other because it's SN2, so it's all happening in one step. And then we're going to do the transition state. So let's start with here. Let's just make things easy. Let's make the bond between oxygen and carbon 2 just a straight line, a straight horizontal line right here. That way we can easily show the orbitals interacting with each other. So that means that we're going to have the bond up here, so that carbon 1 bond right here between carbon 1 and carbon 2. This is going to be R. We can label this as 1 and 2 if that makes it easier. And then we're going to have the nitrogen over here. That's what's going to be attacking the carbon 2. And let's draw the rest of this material. O, and then we can just draw the S and the rest of its bonds up here. not really important for the orbital sketch. So what we want to do is we are breaking the sigma bond between the oxygen and carbon 2. So we are going to show an sp3 orbital for oxygen and for carbon. And we want them to have opposite shading because we want to show that it's breaking. So we're going to have the big lobe for the carbon 2 shaded in, and we're going to have the small lobe for the oxygen shaded in. And we're showing opposite shading, just to make that super explicitly clear. We're showing opposite shading because it's the sigma star CO reactive orbital. We're breaking that bond. And then for NH2, we are taking the lone pair, which is an sp3 orbital for the nitrogen. Maybe that's not good. Maybe we should spread that out a little bit more. Okay, so let's do that. And the H2 is here. And we draw the sp3 that the nitrogen electrons are in. And we want matched shading to show new bond forming. Matched for a new bond. And that is the non-bonding N-sp3 orbital. There. Okay, so that's our orbital interaction sketch. Make sure that over the node, which is at the atom, you switch shading. So one side of each orbital should be unshaded. We could even shade that in a different color, just to make sure you can see that one side is shaded in each orbital. There's one side that's shaded green and one side that's shaded black, and they should be matched if we're forming a new bond or if we have a bond, and they should be oppositely shaded if they are breaking a bond. Okay. Now we're going to draw the transition state with dotted lines for partial bonds. And so as you remember, or should remember, if it's a dashed line, that means that it's a new bond forming or breaking. And we want to make those bonds longer than the normal bonds. So we're just going to try to spread that out so we can show this is oxygen right there. And then this is carbon 1, carbon 2. And then we are also, we're also forming a bond with nitrogen. And so this oxygen here is going to have a partial negative charge because at the end it's going to be negative, right? And so we are breaking this bond and we're giving the electrons to oxygen. The electrons in this bond here are going to oxygen, which is why it's going to have a partial negative. And the lone pair on nitrogen is going to make this bond between the nitrogen and the carbon 2. And so that's going to have a partial positive. And it's going to have a positive charge at the end because it's turning its lone pair to a bond. And so it has one less electron that's kind of around it in a way. And then we're going to show everything else that's connected to the nitrogen. So there's also the H2, and then there's carbon 3 and 4, and then there's the oxygen, sulfur, double bond, oxygen, and oxygen negative. Okay. So yeah, we included partial charges in our transition state. We showed dotted lines for partial bonds. These are the two partial bonds, the ones that are breaking and the ones that are forming. And yeah, and our orbital interaction sketch shows shading and orbital labels. Again, you don't have to actually shade the other side a different color. You didn't have to shade that green. That was just for emphasis. You can do that, but you can just have one side shaded and one side unshaded as long as you're showing matte shading for bonds forming and unmatched shading for bonds that are breaking. Okay. The next question says, draw a curved arrow mechanism for reaction G, resulting in Robaxetine. Use the R group abbreviations defined on the starting material and ignore stereochemistry. So what I'm going to do is we have this circle that was defined for us to make our lives easier for R. What I'm going to do is I'm going to go to the ending material and I'm going to circle that same R so that we know what is changing and what's still the same, because the R group should stay the same since we're using that. And yeah, and then this OH here is going from OH negative to H2O, so that kind of tells us that there might be an acid-base step in here. That's something that we can think about. And we see that this group is coming from here, so we know that that might be leaving at some point. When it does leave, it's going to put the electrons on oxygen, which is why there's going to be another negative charge on another oxygen. Those are just all things to think about. And so, yeah, what will be first? Acid base is usually going to happen first. So let's just draw this starting material with the R group. So we have R, and we have this carbon here. Let's number these 1, 2, 3, and 4. Okay. So this is number 1. That's connected to OH. Let's draw O-H. So we know that there's going to be an acid-base step in there somewhere. 2, nitrogen, hydrogen, that's 3 and 4. And then we have oxygen, sulfur, and there we go. Okay, and we have this OH negative right here. Let's draw the negative next to the oxygen. And so we know that we're going to end up with water at the end. And we see that this oxygen right here must come from this oxygen here, right? Because that's connected. Here, let's draw the numbers on our ending material. There's 1, 2, 3, and 4, right? Because 1 should be the one that's connected to the R group, and it should be connected to the oxygen, and then 2 is next to that, and then 3 is next to the nitrogen, and then 4 is next to that. Okay. So we know that this oxygen here does not have a hydrogen attached to it, so we can kind of guess here that what's going to happen is this OH is going to, well, so OH is going to go ahead and take that hydrogen, and we're going to put the electrons on the oxygen. And this isn't really a favorable or unfavorable step because we're going from an alcohol to water, and so this can happen pretty easily. It's not unfavorable. Either way, it's ROH. They have the same pKa approximately. So, yeah, let's just do that. What does that leave us with? It leaves us with this. We're going to have an oxygen here with a negative charge. There's number 2, nitrogen, hydrogen, 3, 4, and then O, S, O, O, and O negative. Okay. Let's see. So it says, draw a curved arrow mechanism for reaction G resulting in Robaxetine. Well, most of these have been SN2. Do we know for sure that this is going to be SN2? I think it is going to be SN2 because most of these have been SN2 that we've been leading to the ending material. There's no reason why that can't be SN2. That's a good enough nucleophile there. So I think that the leaving group can leave at the same time that the nucleophile attacks. So let's do that. So let's make that leaving group leave, and this oxygen can attack that carbon number 4. Let's label them 1, 2, 3, 4. And then as you can see, we're going to end up with that going to that. We already have water here. That's the other material here. And then what will happen when this oxygen attacks carbon 4? Well, we're going to have a ring with, let's see, what's everything that's going to be in the ring? We're going to have oxygen, carbon 1, 2, nitrogen, carbon 3, and carbon 4 in a ring. And so that's 6-membered ring, where number 1 is attached to R, and yeah, and so that looks exactly like what's going to happen right here, right? Because number 1 is attached to R, the green group, and then number 2 is attached to 1. Number 2 is also attached to nitrogen. Nitrogen's attached to 3. 3 is attached to 4, and 4 will now be attached to the oxygen. And so that's exactly what's going to happen with that curved arrow mechanism. And so that gets us to reboxetine. And we're ignoring stereochemistry anyway, so we don't have to worry about that. So that's the answer for this one. We're getting to our final material. Okay, so the next problem says predict the rate of reaction H relative to the rate of reaction G. So what's different here? Let's circle the R group again. It's going to go up to this. It's going to be our R. So what's different here? Oh, the only thing that's really different is that the sulfur is connected to a CH3 in both of these spots instead of an oxygen. Well, that doesn't really come into play at any point. So I would think that would be the same rate as reaction G. That's the only thing that's changing. Could possibly, let's see what the answer was. It says faster. Okay. And the explanation is because it has a better leaving group because it doesn't already have a negative charge. Okay, so that does make sense, I guess. It's not like a huge change, but because there is no O negative here, that does make sense why it would be a better leaving group, and so it would go a little bit faster because the leaving group leaving is part of the equation for the rate of the reaction. So that does make sense why it would be faster, since that's the only change. Since there's no negative on the leaving group, it's more stable when it leaves. Okay, so that's the last question here on page 4 of midterm 2. Thank you for watching.